You ever get that feeling that something's just off? Like you're playing a video game and there's this weird glitch in the background that nobody else seems to notice, but it keeps happening, and you start wondering if maybe it's not a glitch at all. Maybe it's a feature, a clue to something the developers hid deep in the code. Well, what if I told you that our entire universe has been running with the mother of all glitches for the past 13.8 billion years, and that glitch makes up 95% of everything that exists? Yeah, you heard that right. 95%. Right now, as you sit there watching this video, you're being watched back by something you can't see, can't touch, can't detect with any instrument we've ever built. Something that surrounds you, penetrates you, and binds the galaxy together. No, this isn't the Force from Star Wars, though George Lucas wasn't that far off. I'm talking about dark matter and dark energy, the twin cosmic ghosts that have been haunting physics since we first realized our universe was expanding. And here's the kicker that'll blow your mind. What if these aren't just random mysteries we haven't solved yet? What if they're actually echoes, fossils, gravitational scars left over from a universe that existed before our own Big Bang? What if the reason we can't figure out what they are is because they don't belong to this universe at all? Stick around, because today we're diving down the rabbit hole of one of the most audacious ideas in modern cosmology, that dark matter and dark energy might be relics from a prior universe, messages from a cosmic past so ancient that time itself barely had meaning. We're going to break this down piece by piece, from the basics all the way to the cutting-edge research that's making physicists question everything they thought they knew. And hey, before we get started, do me a huge favor. Smash that like button if you're ready to have your mind blown. Subscribe if you want to join our community of cosmic explorers. And drop a comment below with where you're watching from and what time it is right now. I love seeing how we're all connecting across this pale blue dot, united by our curiosity about the vast darkness beyond. All right, let's begin. So picture this. It's the 1930s, and a brilliant but eccentric Swiss astronomer named Fritz Zwicky is staring at a cluster of galaxies called the Coma Cluster through his telescope at Caltech. Now, Zwicky is what you'd call a character. He called his colleagues spherical bastards, because they were bastards no matter which way you looked at them. But he was also a genius, and what he noticed about this cluster made absolutely no sense. The galaxies inside it were moving way too fast, like way too fast. Think of it like watching cars on a highway. If the highway is just a normal road, cars can only go so fast before they just fly off into the fields. But these galaxies were zipping around like they were on a racetrack with invisible guardrails holding them in place. Zwicky did the math, and the math said that there wasn't nearly enough visible matter, stars, gas, dust, to hold these galaxies together. They should have flown apart billions of years ago. Something invisible was providing the gravity, something massive. He called it Dunkelmaterei, dark matter in German, and then basically got ignored for 40 years because the idea sounded crazy. Let me paint you a fuller picture of this absolute madlet of science, because Fritz Zwicky's story is the kind that makes you realize genius and eccentricity are often two sides of the same coin. Born in Bulgaria to Swiss parents in 1898, Zwicky was the kind of kid who looked at the world and saw puzzles everyone else had missed. He ended up at Caltech in the 1920s, right when astrophysics was becoming a thing you could actually do rather than just philosophize about. But here's the thing about Zwicky. He didn't just think outside the box. He refused to acknowledge the box existed. While other astronomers were carefully cataloging stars and politely debating details, Zwicky was proposing ideas that sounded like they'd been ripped from a pulp sci-fi novel. He once suggested we could extract energy from stars by mixing stellar material with negative mass. He proposed using nuclear explosions to propel spaceships. He even came up with the concept of a gravitational lens in 1937, decades before anyone would actually observe one. The man was living in 3020 while his colleagues were still figuring out 1920. But let's zoom in on that fateful moment with the Coma Cluster, because this is where things get really wild. The Coma Cluster is this massive collection of over 1,000 galaxies sitting about 320 million light-years away from us in the direction of the constellation Coma Berenices. 1930s, Zwicky wasn't looking at it with some puny backyard telescope. He was using the 100-inch Hooker telescope at Mount Wilson Observatory, which at the time was the biggest and baddest telescope in the world. This was the same instrument Edwin Hubble had used to discover that the universe was expanding. Zwicky was studying the individual galaxies in this cluster, measuring how fast they were moving relative to each other, and what he found made his brain short-circuit. The galaxies were moving at speeds averaging around 1,000 kilometers per second. That's about 2.2 million miles per hour. To put that in perspective, that's fast enough to go from Earth to the Moon in about 15 minutes. Now, when you have 1,000 galaxies all moving that fast in a relatively small space, you'd expect them to just shoot off in all directions like billiard balls after a break shot. But they weren't. They were staying together in this tight cluster, bound by gravity. So Zwicky did what any good physicist would do. He calculated how much mass would be needed to hold them together. He added up all the visible matter, the stars glowing in each galaxy, the gas clouds, the dust, everything that could be seen or reasonably inferred. And the number he got was laughably small compared to what was needed. The cluster needed about 400 times more mass than he could see. 400 times. That's not a rounding error. That's a cosmic joke. It would be like looking at a hurricane and calculating that you'd need 400 times more air than you can see to create those winds. Something was massively, fundamentally wrong with the picture. Now here's where Zwicky's genius and his complete disregard for scientific conservatism came into play. Most scientists, when faced with data that contradicted their assumptions, would assume their measurements were wrong. They'd check their instruments, recalibrate their telescopes, blame atmospheric distortion or photographic plates. Not Zwicky. Zwicky looked at the data and said, "No, my instruments are fine. The universe is just weirder than you squares can handle." He proposed that the cluster must contain darkenergy, dark matter, a form of matter that didn't emit, absorb, or reflect light, but had enough gravitational pull to keep everything together. He even speculated it might be those same luminiferous bodies that had been proposed decades earlier but never proven. But here's the tragicomic part. He published this in German in 1933 in a Swiss journal called Helvetica Physica Acta. Then he wrote about it again in 1937 in English in the Astrophysical Journal. And the response from the astronomical community was crickets, absolute silence. Well, not complete silence, more like polite nodding and then everyone going back to their regularly scheduled programming. Why? Because in the 1930s, astronomy was still very much an observational science. If you couldn't see something, it basically didn't exist. The idea that the universe was filled with invisible matter that outweighed visible stuff by 400 to 1 sounded like magical thinking. It violated the principle of parsimony. Don't multiply entities unnecessarily. Occam's razor, the idea that the simplest explanation is usually best, seemed to cut Zwicky's idea to shreds. Maybe you just measured the velocities wrong, they said. Maybe the cluster isn't actually gravitationally bound, it's just flying apart and we happen to be catching it at the right moment, they suggested. Maybe you're just being a spherical bastard, Fritz, they probably thought. So Zwicky's revolutionary insight sat there, gathering dust for 4 decades. He didn't give up. He kept publishing, kept proposing ideas, kept being brilliant and difficult. But the field moved on without him. It would take a woman with the patience of a saint and the determination of a bulldozer to finally drag dark matter back into the spotlight. Now let's talk about Vera Rubin, because her story is just as incredible as Zwicky's, though in a completely different way. Vera Rubin was born in 1928 in Philadelphia, and from the moment she was a kid, she was fascinated by the stars. Her father, an electrical engineer, helped her build a telescope when she was just 14. She was the only student in her high school astronomy class, because she was the only one who signed up. When she wrote to Princeton asking about their graduate program in astronomy in 1948, they sent her a brochure for their graduate program in astronomy for women. Spoiler, Princeton didn't admit women to their astronomy program until 1971. That gives you just a taste of what she was up against. Rubin ended up at Cornell for her master's degree, where she studied under some of the greats, then got her PhD at Georgetown. But here's the thing. The entire time she was fighting an uphill battle. In the 1950s and 1960s, astronomy was a boys' club. Women weren't given telescope time at major observatories. They weren't hired for faculty positions. They were expected to be assistants, not principal investigators. When Rubin applied to use the Palomar Observatory in the 1960s, she had to fight just to get access. When she showed up, there was no women's restroom, because there had never been a woman observer there before. She had to cut out a cardboard figure of a woman and tape it to the men's room door. That's the level of institutional sexism we're talking about. But Rubin had this quiet, unshakable determination. She wasn't loud or confrontational like Zwicky. She was methodical, precise, and relentless. She chose to study something that seemed straightforward: galaxy rotation. The logic was simple and went back to Newton. In any gravitational system, things that are closer to the center should orbit faster than things farther out. That's why Mercury orbits the Sun every 88 days while Neptune takes 165 years. The gravitational pull is weaker the farther out you go, so you need less speed to stay in orbit. This had been confirmed over and over in our solar system, and everyone assumed it would hold true for galaxies too. So Rubin started measuring the rotational speeds of spiral galaxies. She used spectroscopy, breaking down the light from different parts of a galaxy to see how much it was shifted by the Doppler effect. Light from the side of a galaxy rotating toward us gets compressed to bluer wavelengths, blue-shifted, while light from the side rotating away gets stretched to redder wavelengths, red-shifted. By measuring this shift, you can calculate how fast each part of the galaxy is moving. And what she found over and over made absolutely no sense. The rotation curves, graphs showing speed versus distance from the center, were supposed to drop off at the edges. They didn't. They stayed flat. The outer stars were moving just as fast as the inner stars. It was exactly like that merry-go-round analogy. The wooden horses on the outer ring were keeping perfect pace with the horses near the center, which should be physically impossible unless there was some invisible structure, a hidden track, invisible rails, some cosmic scaffolding, holding the whole thing together. Rubin studied galaxy after galaxy. She used better telescopes, better instruments, better techniques. She collaborated with her colleague Kent Ford, who had built an incredibly sensitive spectrograph. They measured the rotation curves of dozens of spiral galaxies, Andromeda, Triangulum, NGC 2403, and many more, and every single one showed the same impossible pattern. The data was irrefutable. The error bars were tiny. The signal-to-noise ratio was excellent. This wasn't a measurement problem. This was a reality problem. Now here's where Rubin's genius really shines through. She didn't immediately jump to exotic explanations. She checked everything. Could the stars be moving in some weird non-circular orbits? No, the data didn't support that. Could there be some unseen normal matter, gas, dust, faint stars, that we just weren't accounting for? She added up every possible source of normal matter, and it still came up short by a factor of 5 or 6. Not 400 like Zwicky's clusters, but still, you needed 5 or 6 times more mass than you could see. And then she made the connection. She was aware of Zwicky's work. Astronomers knew about it, even if they dismissed it. And she realized that her data on individual galaxies was showing the same problem as Zwicky's data on galaxy clusters, just on a smaller scale. The same invisible matter that held clusters together must be holding galaxies together too. It wasn't a fluke. It was a feature of the universe. Rubin presented her findings at conferences, published them in major journals like the Astrophysical Journal. And even then, the response was slow. Science is conservative by nature. People didn't want to accept that the universe was mostly invisible, but Rubin had something Zwicky didn't have: decades of meticulous, consistent data across many galaxies. She had the Hubble Space Telescope launching in 1990, which would eventually provide stunning visual confirmation. She had the rise of radio astronomy and infrared astronomy, which could detect matter that optical telescopes missed. And most importantly, she had the sheer weight of evidence that couldn't be ignored forever. By the 1980s, the tide was turning. Computer simulations of galaxy formation showed that you couldn't form spiral galaxies without dark matter. Observations of gravitational lensing, where massive objects bend light from background sources, showed that galaxies had way more mass than their stars could account for. The cosmic microwave background radiation, mapped by satellites like COBE and WMAP, showed that the universe's structure could only be explained if dark matter existed. But here's something that often gets lost in the retelling. What Rubin discovered was actually even weirder than just dark matter. The distribution of this invisible stuff had to be completely different from normal matter. Normal matter, stars, gas, dust, clumps together in the center of galaxies, creating that bright bulge you see in photos. But dark matter needed to be spread out in a vast halo, extending far beyond the visible galaxy. The rotation curve stayed flat out to distances where there were almost no stars, which meant the dark matter halo had to be enormous, maybe 10 times the size of the visible galaxy. This invisible halo isn't just some minor addition, it's the main structure, and the galaxy we see is just a tiny, bright ornament floating in the center of this vast dark cloud. Let me give you a sense of scale that will absolutely break your brain. The Milky Way's visible disk is about 100,000 light-years across, but the dark matter halo that surrounds it might be more like 1 million light-years across. That means if you could see dark matter, our galaxy would look like a tiny frisbee floating in the center of an invisible sphere the size of, well, the size of something so huge it's hard to comprehend. And this invisible sphere outweighs the visible galaxy by about 5 to 1. Every star you can see, every nebula, every beautiful Hubble image, it's all just the frosting on a dark matter cake. What's even more mind-bending is that dark matter doesn't seem to interact with itself either. When galaxy clusters collide, as in the famous bullet cluster observation, the dark matter just passes right through other dark matter, while the normal gas gets stuck in the middle. It's like ghosts passing through ghosts. This collisionless behavior is one of the key pieces of evidence that dark matter isn't just normal matter we can't see. It's something fundamentally different. Now let's jump ahead again, this time to 1998. Two independent teams of astronomers are studying distant supernovas, exploding stars that act as cosmic lighthouses, letting us measure distances across the universe. They expected to find that the universe's expansion was slowing down over time because gravity pulls things together. Makes sense, right? If you throw a ball up, it slows down and comes back down because of gravity. Everyone expected the universe to be like that ball, gradually slowing down after the Big Bang. But what they found instead made them question reality itself. The supernovas were too faint, which meant they were farther away than they should be. The only explanation: the universe's expansion isn't slowing down, it's speeding up. Something is pushing everything apart and it's getting stronger. They called this mysterious force dark energy, and it turns out to be even weirder than dark matter. Because while dark matter pulls things together with gravity, dark energy does the opposite. It pushes everything apart with what physicists call negative pressure. Here's where the numbers get absolutely bonkers. When we look at the total energy budget of the universe, the cosmic ledger that tells us what everything is made of, we find that normal matter, the stuff that makes up you, me, stars, planets, everything we've ever touched or seen or loved, accounts for just 5% of the total. 5%. Dark matter makes up about 27%, and dark energy makes up a whopping 68%. We are the minority. We are the cosmic afterthought. The universe is dominated by things we don't understand at all. And that's not just a minor gap in our knowledge. That's like trying to understand the ocean when you can only see the surface foam. We've built the Large Hadron Collider. We've launched the James Webb Space Telescope. We've created detectors deep underground and sent satellites into orbit. And we still haven't directly detected a single dark matter particle or figured out what dark energy actually is. It's the biggest embarrassment in modern physics, and it's been driving scientists crazy for decades. But what if we've been asking the wrong question? What if the reason we can't detect dark matter particles isn't because our detectors aren't sensitive enough, but because dark matter isn't made of particles at all, at least not particles from this universe? What if dark energy isn't some new force, but a kind of cosmic echo, a gravitational memory from a previous cycle of existence? This is where things get really wild, and we need to talk about what might have happened before the Big Bang. Now, most people think the Big Bang was the beginning of everything. The moment when time started, space was born, and all matter and energy came into existence from nothing. But here's a secret that physicists whisper about in late-night conversations. The Big Bang isn't necessarily the beginning. It's the beginning of our universe as we know it, yes, but it might not be the beginning of everything. There are now serious, mathematically rigorous theories that suggest our universe is just one in a long series of universes, a cosmic cycle of birth, death, and rebirth that stretches back into a past so ancient that our universe is just the latest chapter in a story that's been told countless times before. One of the most compelling of these theories is called the bouncing cosmos, or non-singular matter bouncing cosmology, and it's exactly what it sounds like. Instead of starting from a singularity, a point of infinite density where the laws of physics break down, this theory suggests that our universe came from a previous universe that was contracting. Picture a universe that's slowly shrinking, getting denser and hotter, until it reaches a point where it can't shrink anymore. But instead of collapsing into a singularity, it bounces. It rebounds. And that rebound is what we call the Big Bang. The universe before ours contracted down to a size that's 50 orders of magnitude smaller than what we see today, unimaginably tiny, but not infinite, not a singularity where physics fails. And then it bounced back, creating the expanding universe we live in now. Now here's where dark matter comes into this story. In these bouncing cosmology models, when the universe is at its most contracted state, right near the bounce, matter becomes so incredibly dense that quantum fluctuations, those tiny, random jitters in the fabric of spacetime that we know exist from quantum mechanics, can actually create black holes. Not giant black holes like the ones that form when stars collapse, but tiny, primordial black holes, some weighing no more than an asteroid. These black holes would have formed in the fireball of the bouncing universe, and if they're massive enough, they wouldn't have evaporated away through Hawking radiation, the process by which black holes slowly lose mass and eventually vanish. Instead, they'd still be around today, billions of years later, invisible except for their gravitational pull. Sound familiar? These primordial black holes would behave exactly like dark matter. They'd be invisible because they don't emit light. They'd be massive. They'd provide gravitational glue holding galaxies together. And they'd be impossible to detect directly because they're just black holes floating in space, not particles. Patrick Peter, a director of research at the French National Center for Scientific Research who studies these models, explains that these small primordial black holes could be produced during those very early stages. And if they're not too small, Hawking radiation won't be efficient enough to get rid of them. Weighing more or less the mass of an asteroid, they could contribute to dark matter, or even solve the dark matter problem entirely. The calculations from these bouncing cosmology models show that the resulting universe would have properties, like the curvature of space and the pattern of the cosmic microwave background radiation, that afterglow of the Big Bang we can still see today, that match our current observations perfectly. This isn't some crackpot theory. It's a mathematically consistent model that explains what we see without inventing new particles we've never detected. But what about dark energy? How could that be a relic from a previous universe? This is where things get even stranger. In these cyclic models, each universe leaves behind a kind of gravitational imprint on the fabric of spacetime itself. Think of it like writing on a whiteboard. If you erase the board, you can still sometimes see the ghost of what was written there before, faint impressions in the surface. What if dark energy is like that? A faint impression left by the gravitational field of the previous universe, a kind of cosmic memory that persists even after the universe has died and been reborn. This gravitational scar would manifest as a repulsive force, a negative pressure that pushes everything apart, exactly what we observe as dark energy. Now, I know this sounds like science fiction, but there's actually a growing body of research exploring these ideas. Dr. Richard Liu, a physics professor at the University of Alabama in Huntsville, recently published a paper proposing a model of the universe built on what he calls transient temporal singularities. Essentially, sudden bursts of matter and energy that appear and disappear throughout the cosmos. These singularities would be unobservable because they happen so rarely and so quickly, but their cumulative effect would be to create both the gravitational pull we attribute to dark matter and the repulsive push we call dark energy. Liu's model doesn't require exotic particles or negative mass. It just requires that the universe is more complicated than our simple models assume. He notes that these singularities could be the reason why dark matter and dark energy haven't been found. They're not continuous things you can detect, but intermittent flashes that average out to create the effects we see. Interestingly, Liu's work echoes an idea from the famous astronomer Fred Hoyle, who opposed Big Bang cosmology and proposed a steady-state model, where matter is constantly created as the universe expands. Hoyle's model violated the conservation of mass energy, but Liu's version gets around that by having matter appear and disappear in sudden bursts, maintaining conservation on average. The origin of these temporal singularities is unknown, but Liu points out that the same is true of the Big Bang itself. We don't know what caused it, so we're just pushing the mystery back one step further. But wait, there's more. Another group of researchers, led by Professor David Wiltshire at the University of Canterbury in New Zealand, has proposed that dark energy might not exist at all, not because it's a relic from a previous universe, but because we've been misinterpreting our observations. Their timescape model suggests that the universe's expansion appears to be accelerating not because of some mysterious force, but because time itself flows at different rates in different parts of the cosmos. In dense regions like galaxy clusters, gravity slows time down. In the vast empty voids that make up most of the universe's volume, time runs faster. According to their calculations, a clock in the Milky Way would tick about 35% slower than an identical clock in one of those cosmic voids. This means that billions more years have passed in the voids, allowing them to expand more. When we measure the expansion rate using supernovas, we're comparing clocks that aren't synchronized, which creates the illusion of acceleration. Dark energy, in this view, is a misidentification of variations in the kinetic energy of expansion in a universe that's lumpy rather than perfectly smooth. This timescape model is particularly interesting because it directly challenges the standard lambda-cold dark matter model, or lambdictum, which has been the backbone of cosmology for decades. The lambdictum model assumes that on average, the universe is uniform, the so-called cosmological principle. It uses dark energy, represented by the Greek letter lambda, and cold dark matter to explain what we see. But recent observations have been poking holes in this model. The Hubble tension, for instance, is a major discrepancy between the expansion rate we measure from the early universe using the cosmic microwave background and the rate we measure from nearby supernovas. These two values should agree, but they don't. They differ by about 10%, which is huge in cosmology. The Dark Energy Spectroscopic Instrument, DAISY, has also found that the lambda model doesn't fit the new high-precision data as well as models where dark energy evolves over time rather than staying constant. These tensions suggest that our standard picture is incomplete at best, flat wrong at worst. And then there's the James Webb Space Telescope, which has been throwing wrenches into our understanding of galaxy formation. JWST has discovered galaxies in the very early universe that are far too massive and too well developed to have formed so quickly after the Big Bang. Some of these galaxies existed just 500 million years after the Big Bang, but they look like they should have taken billions of years to evolve. It's like finding a fully grown adult in a nursery full of newborns. These observations have sparked intense debate. Some astronomers, like Rohan Naidu at MIT and Gyuachao Sun at the Harvard-Smithsonian Center for Astrophysics, have been on the front lines of these discoveries. Naidu says that from the observational side, we've gotten much more detailed data, and it's now clear that these galaxies are a bona fide class of galaxies. They exist in numbers that are very uncomfortable for all the models we had before JWST. Before the telescope launched, theoretical models indicated that such galaxies should be extremely rare, but now we're seeing them everywhere. This is where early dark energy theories come into play. Some researchers wondered if dark energy wasn't always constant. What if there was a burst of early dark energy in the first moments after the Big Bang that affected how galaxies formed? Shen and Naidu collaborated with other astrophysicists to run computer simulations incorporating early dark energy, and they found that the repulsive force of this early dark energy would have impacted the distribution of dark matter, the scaffolding that normal matter clumps onto to form galaxies. If dark matter was distributed differently because of early dark energy, it could explain why those massive galaxies formed so quickly. This is a perfect example of how mysterious dark components might be interconnected in ways we don't yet understand. But let's get back to our main story, the idea that dark matter and dark energy are relics from a prior universe. This concept is part of a broader class of theories called cyclic cosmologies. The most famous of these is the ekpyrotic universe model, which suggests our universe is one of two three-dimensional brains, like sheets of paper, floating in a higher dimensional space. These brains periodically collide, and each collision creates what looks like a big bang from our perspective. The cycle repeats forever: collision, expansion, contraction, collision again. In this model, the dark matter and dark energy we see could be remnants from the previous cycle, gravitational effects that persist across the collision. Another variant comes from string theory and what some call the conformal cyclic cosmology, proposed by Nobel laureate Roger Penrose. He suggests that the universe goes through infinite cycles, and each cycle leaves behind imprints in the cosmic microwave background that could be detected as patterns of concentric circles. While Penrose's specific predictions haven't been confirmed, the idea that information could survive from one universe to the next is taken seriously by theoretical physicists. The key insight here is that our universe might not be a freshman with no past. It might be a senior with a rich history, carrying baggage from previous lives. That baggage could be dark matter and dark energy. Think of it like geological strata on Earth. When you dig down, you find layers from different eras, each leaving its mark on the planet. Dark matter could be like ancient bedrock, formed in the intense conditions of a previous universe's final moments, so dense and compact that it survived the bounce and now exists as invisible gravitational anchors. Dark energy could be like fossilized ripples, imprints of the previous universe's expansion, frozen into the fabric of spacetime, and now manifesting as a gentle but relentless push, driving everything apart. Now you might be thinking, this is all very interesting, but where's the proof? How can we test these crazy ideas? Great question, and I'm glad you asked because this is where the story gets really exciting. Physicists are developing ways to test these theories, and some of them might bear fruit within the next decade or two. First, there's the gravitational wave approach. The bouncing cosmology models that predict primordial black holes as dark matter also predict a specific signature of gravitational waves, ripples in spacetime itself, that would have been produced when those black holes formed. The researchers who developed this model calculated the exact properties of these gravitational waves, and they found that they fall within the detection range of upcoming observatories like the Laser Interferometer Space Antenna, LISA, and the Einstein Telescope. LISA is a space-based gravitational wave detector consisting of 3 spacecraft flying in formation, set to launch in the 2030s. The Einstein Telescope is a ground-based observatory planned for Europe. If these detectors find the specific pattern of gravitational waves predicted by the bouncing cosmology model, it would be strong evidence that primordial black holes from a previous universe are indeed the dark matter we've been searching for. However, it could take more than a decade before either facility sees first light, so we need to be patient. Second, there's the ongoing hunt for dark matter particles. Despite decades of searching, experiments like Edelweiss in France, Xenon in Italy, Lux in the United States, and PandaX in China have found nothing. These experiments are designed to detect weakly interacting massive particles, or WIMPs, which have been the leading candidate for dark matter for years. The fact that we haven't found them yet could mean they don't exist, or it could mean we need more sensitive detectors. But it could also mean we've been looking for the wrong thing entirely. If dark matter is primordial black holes, we'll never detect them with these particle detectors because black holes aren't particles. They're regions of warped spacetime. The way to detect them would be through gravitational lensing, the bending of light from distant galaxies by massive objects. We've already seen this effect in the Bullet cluster, which provided some of the best direct evidence for dark matter. In 2006, astronomers observed this galaxy cluster, which formed when 2 clusters collided. Using NASA's Chandra X-ray Observatory, they mapped the hot gas normal matter in pink. Using gravitational lensing observations from the Hubble Space Telescope and the Giant Magellan Telescope, they mapped the mass, mostly dark matter, in blue. The dark matter had passed right through the collision while the normal matter got stuck in the middle, proving that whatever dark matter is, it doesn't interact with itself or normal matter except through gravity. If dark matter is primordial black holes, this behavior makes perfect sense. Third, we have the cosmic microwave background, or CMB, the faint afterglow of the Big Bang that we can still detect with microwave telescopes. The CMB is like a baby picture of the universe, showing us what it looked like when it was just 380,000 years old. The patterns in the CMB have been used to confirm the standard lambda model with incredible precision. But some researchers are looking for anomalies in the CMB, patterns that shouldn't be there if the standard model is correct. For example, there are unexplained cold spots and asymmetries that some cosmologists have suggested could be bruises from collisions with other universes in a multiverse scenario. While this is highly speculative, future CMB missions with higher resolution could potentially detect signatures that support cyclic cosmologies. Fourth, there's the approach of modifying gravity itself. If dark matter and dark energy are artifacts of a previous universe, maybe the laws of gravity were also inherited and aren't exactly what Einstein described. This leads us to theories like MOND, modified Newtonian dynamics, which suggests that gravity behaves differently at very low accelerations, like those at the edges of galaxies. While MOND has had some success explaining galaxy rotation curves, it struggles with larger-scale phenomena like galaxy clusters and the cosmic microwave background. However, more sophisticated versions like TVS, tensor vector scalar gravity, have been developed. Another radical approach is Eric Verland's entropic gravity, which suggests gravity isn't a fundamental force at all, but an emergent phenomenon that arises from the thermodynamics of information encoded in spacetime. In Verland's model, dark matter is an illusion created by the interplay between dark energy and normal matter. While still incomplete, this theory has successfully reproduced the rotation curves of spiral galaxies without any dark matter particles, showing that there are multiple ways to interpret the data. Now, let's talk about some of the problems with these alternative theories, because science is all about being skeptical and testing ideas against reality. The bouncing cosmology model with primordial black holes as dark matter is elegant, but it needs to explain why these black holes would have the right masses and abundances to match observations. Too many black holes and they'd disrupt galaxy formation. Too few and they wouldn't account for all the dark matter we need. The model also needs to explain the precise spectrum of gravitational waves we'd expect to see. While the researchers have made predictions, these haven't been tested yet. The timescape model that eliminates dark energy by having time flow at different rates is also elegant, but it needs to explain all the other evidence for cosmic acceleration, including the detailed patterns in the cosmic microwave background and the large-scale distribution of galaxies. It's one thing to explain supernova data, but the model needs to match all observations across all scales. So far, it's promising but not yet definitive. Liu's temporal singularities model is fascinating, but it raises its own questions. What causes these singularities? Why do they appear and disappear? The model pushes the mystery of the Big Bang back to the mystery of the singularities, which some critics argue is just trading one unknown for another. Still, the fact that it can explain both dark matter and dark energy with a single mechanism makes it worth investigating. And the standard lambdictum model, despite its tensions, still explains an enormous amount of data with incredible precision. The Hubble tension and JWST discoveries are real problems, but they could be resolved through observational errors, unknown systematic effects, or subtle modifications to the standard model that don't require throwing it out entirely. Science often progresses by patching holes rather than building entirely new houses. So where does this leave us? Let me paint you a picture of the current landscape. On one side, we have the standard model of cosmology, a universe that began in a Big Bang, filled with cold dark matter particles we haven't detected yet, and dominated by dark energy that's either a cosmological constant, an inherent property of empty space, or some kind of dynamical field. This model matches most observations but has serious tensions with new data. On another side, we have cyclic cosmologies, universes that bounce, contract, and expand in endless cycles, carrying relics from previous epochs in the form of primordial black holes and gravitational imprints. These models naturally explain dark matter and dark energy, but lack definitive observational proof. On yet another side, we have radical reinterpretations. Maybe dark energy doesn't exist, and it's just an effect of time flowing differently in different places. Maybe gravity itself emerges from information theory. Maybe temporal singularities flood the cosmos with invisible matter and energy. And threading through all of this is the incredible fact that we can even ask these questions. We're living in a golden age of cosmology. We have the James Webb Space Telescope peering deeper into space and time than ever before. We have LISA and the Einstein telescope coming online in the next decade to detect gravitational waves from the dawn of time. We have DAISY mapping millions of galaxies to understand cosmic structure. We have underground detectors waiting for dark matter particles that might never come. We have computer simulations running on supercomputers modeling galaxy formation with different assumptions. We're throwing everything we have at this problem. I want you to really appreciate how strange and wonderful this moment is. For most of human history, we thought the Earth was the center of everything. Then we learned we're orbiting an ordinary star on the outskirts of an ordinary galaxy in an ordinary universe. Now we're learning that our universe might be just one chapter in an infinite book, and that most of that book is written in invisible ink. The dark matter that holds your galaxy together and the dark energy that will eventually tear your supercluster apart might both be messages from a universe that died billions of years before our own was born. You're not just a citizen of Earth or a resident of the Milky Way. You're an inheritor of a cosmic legacy that spans cycles of creation beyond imagination. Think about what this means for the ultimate fate of the universe. If the standard model is right and dark energy is a cosmological constant, then the universe will end in a big freeze or heat death. The expansion will continue forever, accelerating until all galaxies are pulled apart from each other. Stars will burn out, black holes will evaporate, and the universe will become a cold, dark, empty place where nothing ever happens. But if dark energy is a relic from a previous universe, it might not be constant. It might evolve, strengthen, or weaken over time. It could lead to a big rip, where dark energy becomes so powerful that it tears apart galaxies, solar systems, planets, and eventually atoms themselves. Or it could fade away, allowing gravity to take over and causing a big crunch, where the universe collapses back in on itself, setting the stage for another bounce and another cycle. Or in the cyclic models, the expansion might slow, reverse, and contract, leading to a new Big Bang and a fresh start. Your atoms, which were forged in stars that died billions of years ago, might one day be part of a new universe's first generation of stars. Let me give you another analogy to make this concrete. Imagine you're an archaeologist in Egypt and you discover a pyramid. You can study its stones, measure its dimensions, and analyze its structure. But the pyramid itself is just the visible part of a much larger story. Beneath it, there are older structures, layers of previous civilizations, each leaving behind artifacts and foundations. The pyramid is built on top of these earlier layers. In cosmology, the visible universe, stars, galaxies, nebulae, is like that pyramid. Dark matter and dark energy are like the hidden layers beneath, remnants of earlier cosmic epochs. We're trying to understand the pyramid without digging, but now we're developing the tools to excavate. The gravitational wave detectors like LISA are our shovels. The cosmic microwave background anomalies are our hidden chambers. The JWST's impossible galaxies are our secret passages. Each piece of evidence is helping us reconstruct the history not just of our universe, but of the universes that might have come before. Now I want to address something important. When you hear theories like this, it's natural to be skeptical. You should be skeptical. Science is built on skepticism. The difference between science and pseudoscience is that science makes testable predictions. These cyclic cosmology models predict specific gravitational wave signatures that we can look for. They predict specific patterns in the CMB. They predict specific abundances of primordial black holes. If we don't find these signatures, the models are wrong and we move on. That's how science works. We're not just making up stories. We're making educated guesses based on mathematics and then testing them against reality. And here's something else to consider. Even if these specific models turn out to be wrong, they might be pointing us in the right direction. The history of science is full of wrong theories that led to the right answer. The ancient Greek idea of atoms was wrong in its details, but right in its core insight that matter is made of indivisible particles. The plum pudding model of the atom was wrong, but led to Rutherford's discovery of the nucleus. Steady-state cosmology was wrong but highlighted problems with the Big Bang model that needed to be solved. These cyclic models, even if they're not exactly right, are telling us that we need to think bigger, that we need to consider the possibility that our universe has a history before the Big Bang. So what should you take away from all this? First, that the universe is far stranger and more mysterious than everyday experience suggests. The fact that you're sitting there watching this video on a device that works because of quantum mechanics, while dark matter holds your galaxy together and dark energy pushes the universe apart, is a testament to how weird reality is at its deepest levels. Second, that science is a process of discovery, not a collection of facts. What we know today might be overturned tomorrow by a new observation or a better theory. And third, that you are living in one of the most exciting times in human history for understanding our place in the cosmos. The questions we're asking now, about dark matter, dark energy, and what came before the Big Bang, are questions that might be answered within your lifetime. I want you to imagine what it would feel like if we actually detected those gravitational waves from primordial black holes. Picture the press conference, the headlines. Scientists confirm existence of previous universe. Imagine looking up at the night sky, knowing that the darkness between the stars isn't empty. It's filled with the gravitational ghosts of a cosmos that died so ours could be born. That the same force that will eventually tear apart your galaxy is a memory of an expansion that happened billions of years before time began. It's a profound, humbling, and strangely beautiful thought. And what if we instead confirm that dark energy is just an illusion created by time flowing differently in different places? That would mean our universe isn't accelerating at all. We're just miscalibrating our cosmic clocks. The universe's ultimate fate might be very different from what we currently think. It might expand forever but slowly, or it might eventually contract. The certainty we thought we had would evaporate, and we'd need to start over. Or maybe we do find dark matter particles. Maybe one of those underground detectors finally sees a WIMP, and we build a factory to produce them, and we learn that they're just another particle in the Standard Model's extended family. That would solve one mystery but leave the door open for others. Why does dark matter exist? What role does it play in the grand scheme? Is it connected to dark energy in some deeper way? The point is, we don't know, and that's okay. In fact, that's wonderful. The universe is still a mystery, and we get to be the generation that might solve it, or at least we get to be the generation that asks the right questions. Before we wrap up, let's do a quick recap of everything we've covered, just to make sure it's all clear. Dark matter is invisible stuff that holds galaxies together. We know it exists because of galaxy rotation curves, gravitational lensing, and observations of galaxy clusters like the Bullet Cluster. Dark energy is a mysterious force pushing the universe apart faster and faster. We know it exists because distant supernovas are fainter than they should be, indicating the expansion is accelerating. Together, they make up 95% of the universe, and we have no idea what they are. The standard explanation is that dark matter is made of unknown particles, and dark energy is a cosmological constant, a property of empty space. But this model has problems. The Hubble tension, the impossible early galaxies seen by JWST, and the fact that we haven't detected any dark matter particles despite decades of searching. Alternative theories suggest that dark matter might be primordial black holes formed in a previous universe that bounced back to create ours. Dark energy might be a gravitational scar from that previous universe's expansion, or an illusion created by time flowing at different rates, or the result of temporal singularities that appear and disappear throughout the cosmos. We can test these theories with gravitational wave observatories like LISA and the Einstein telescope, with more precise measurements of the cosmic microwave background, with JWST's observations of early galaxies, with DAISY's maps of cosmic structure, and with next-generation dark matter detectors. The next decade or two could revolutionize our understanding. Now, I want to leave you with one final thought that might keep you up at night. If dark matter and dark energy are relics from a previous universe, then everything we see, every star, every galaxy, every atom in your body, is made from recycled material. The hydrogen in your DNA was forged in the Big Bang, but the dark matter holding your galaxy together might be from a Big Bang that happened trillions of years before. You are not just a child of this universe. You are a grandchild of countless universes, a living embodiment of a cosmic lineage that stretches back beyond time. The darkness above you when you look up at the night sky isn't empty. It's a museum of ancient history, and we're just now learning how to read the exhibits. If that doesn't make you feel connected to something larger than yourself, I don't know what will. All right, my fellow cosmic explorers, we've reached the end of our journey today. We've traveled from the swirling galaxies of the Coma Cluster to the quantum foam of the bouncing cosmos, from Vera Rubin's telescopes to the gravitational wave detectors of the future. We've confronted the possibility that our universe is just one chapter in an infinite library, and that the darkness we see is actually full of ghosts. I hope this video has given you a new appreciation for the mystery and majesty of existence. I hope you'll look up at the night sky tonight with fresh eyes, wondering not just about the stars you can see, but about the invisible forces that shape everything. And I hope you'll join me in staying curious, asking big questions, and never being satisfied with easy answers. Now, before you go off to ponder the fate of your atoms in some future universe, I want to ask you personally, if you found this journey fascinating, if your mind is spinning with possibilities, please take a second to hit that like button. It really helps the channel grow and brings more cosmic content to curious minds like yours. If you haven't subscribed yet, consider joining our family of stargazers and deep thinkers. We've got so much more to explore together. And definitely drop a comment below with where you're watching from and what time it is. I read every single comment, and I love seeing our community stretch across this pale blue dot, from midnight watchers in Mumbai to early morning viewers in Melbourne, from sunset streams in Seattle to sunrise sessions in Santiago. You make this journey worthwhile. As you close your device and step away from this video, I want to leave you with this. The universe is vast, dark, and mostly empty, but it's also beautiful, mysterious, and possibly eternal. Whether dark matter is primordial black holes from a previous universe or some exotic particle we haven't discovered, whether dark energy is a gravitational scar or a trick of time, the fact that we can even ask these questions is a profound gift. Don't take it for granted. Stay curious, stay humble, and keep looking up. From wherever you are on this tiny world, hurtling through the darkness at unimaginable speeds, held together by mysteries we barely understand, I want to say thank you for spending this time with me. Thank you for being brave enough to confront the unknown. Thank you for being part of this grand adventure. Goodbye, my friends. And if it's night where you are, sleep well under those ancient stars. If it's day, step outside and feel the sunlight, photons that journeyed from the sun's surface, through the dark matter halo of our galaxy, across the expanding void of dark energy, just to warm your skin. That's the universe reaching out to you, reminding you that you are part of something extraordinary. Good night wherever you are, and remember, the greatest discoveries are yet to come. Sweet dreams, cosmic wanderers. See you in the next video.